Now let's do another example that is just a slightly more complicated. So we'll look at the O2 molecular orbital diagram. This gets more complicated because oxygen is in the second row. It has both the 2s and the 2p shells as valence electron shells. So our molecular orbital diagram will be a bit larger. We're still working on the energy scale. And recall that the s orbitals are lower energy than p, so we'll put, well, let's remember we have 2 oxygen atoms. It has the 2s valence shell and the 2p valence shell. Now we already talked about how the s shells can overlap. They can overlap to form a sigma and a sigma star orbital. I'm getting a little ahead of myself. Let's put in the the electrons in the atomic orbitals. Oxygen is the 6th element in the 6th column, so it has 6 valence electrons. We fill the lower energy atomic orbital first, so that takes care of 2, and then we have 4 more in the 2p orbital. And I'm just looking at the periodic table to find the number of electrons. So it has 2 in the 2s shell and then 4 in the 2p shell. And I do want to scroll up and look at this Hund's rule, which says orbitals of the same energy will be singly occupied before doubly occupied. So that means when I'm putting 4 electrons into the oxygen 2p orbital, I'll put 1 in each 2p orbital. We have px, py, and pz. I'll draw those out in a minute. And then I'll double up for that last electron. So each oxygen atom has 6 electrons in its valence shell. I'll do the same thing for the oxygen atom on the right. And you could put that last electron in any of the 2p orbitals. It really doesn't matter. Okay, so we talked about how the 2s shell can overlap to form sigma and a sigma star orbital. Now the 2p valence shells, or the p valence shells, are shaped differently. So as we think about the 2p orbitals, or the p orbitals in general, we have, now I'm drawing this on the side, we have a px orbital. Let's write out our 3D graph here. So we have x going left and right in the plane of the paper, y up and down in the plane of the paper, and then z is going, that's the third dimension, away from us towards us, depending on how you're looking. So if our px orbital is on the x-axis, we have the 2 lobes along the x-axis. And in p orbitals, one is in phase, and we can write that as shading, one is out of phase. The py orbitals are up and down in the plane of the paper. Again, one is in phase, one is out of phase. And then pz coming towards us and away from us. One is in phase, one is out of phase. So if we have p orbitals from 2 different atoms that are overlapping, we can create from each p orbital, px, py, and pz, we can create a bonding, and we'll draw that in, and antibonding orbitals, molecular orbitals. So if we bring in another px orbital from another atom, like two oxygen atoms, those can bond as long as the two lobes that are in the same phase overlap. If we have the opposite, so I'm going to draw the same original px orbital, we have now out of phase overlapping with in phase, that would be the antibonding orbital. And because the orbitals are directly overlapping in a line where one lobe is overlapping from each px orbital, this is also called a sigma molecular orbital, a sigma bond. If we have two atoms with p orbitals, when the py orbitals overlap to form a bonding orbital, they overlap in the y direction. And in this case, we have both lobes from the p orbitals overlapping. So this is not called a sigma bond or a sigma molecular orbital. This is now a pi molecular orbital. And this looks just the opposite phasing if we have antibonding. And then you could probably predict what the PZ will look like for a bonding orbital. We have the same phasing overlapping. This is again a pi bond. And for antibonding, we have opposite phases overlapping. And this would be a pi star. Py antibonding is pi star, and then Pz antibonding is sigma star. So that's what the orbitals actually look like in space, the shape of the orbitals. And we can use all of that to now fill in the molecular orbital diagram for O2, for dioxygen. We are going to put the px sigma bonding orbital as lower energy than the 2p. And the sigma p molecular orbitals are also different energy from the sigma pi molecular orbitals. For oxygen, we'll have the sigma a little bit lower energy than the pi molecular orbitals. Now, the two pi molecular orbitals are the same energy as each other. So we'll put those in the same energy plane. And then we can draw the opposite, where we have the pi antibonding orbitals of the same energy. So these are pi star, and the sigma antibonding orbital. All right, let's make sure we have the right number of molecular orbitals. So each oxygen atom starts with 4 atomic orbitals, the 2s, and then each of the 3 2p orbitals. So that's 8 total because we have 2 electron atoms. Now let's count our molecular orbitals. Starting from the 2s sigma, we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 molecular orbitals, we're good to go. Our next step is to fill in electrons. Filling lowest energy first, following all these rules. So we fill lowest energy first. We cannot have 2 electrons with the same spin. And orbitals of the same energy will be singly occupied before doubly occupied. So we can fill in 2s orbital, 2s sigma orbital, that's 2 electrons, 2 more in the sigma star. So we've taken care of 4 electrons so far. We need to add a total of 12 electrons. So we have 4. Now we can add 5, 6, 7, 8, 9, 10, 11, 12. So there we have all 12 valence electrons in the dioxygen molecule filled in the appropriate molecular orbitals. So let's now calculate O2 bond order. And we'll get all of the electrons in bonding orbitals. So here we have 2, 4, 6, 8 electrons in bonding orbitals. And then subtract all of the electrons in antibonding orbitals. That is 4 electrons in antibonding orbitals divided by 2 is 4 divided by 2, which is a bond order of 2. Now that means the bond between oxygen and dioxygen is a stronger bond because it has a higher bond order than the bond between hydrogen and dihydrogen, which has a bond order of 1. And again, this aligns with our Lewis structure of dioxygen, where we have a double bond between the 2 oxygen atoms, and that aligns with having a bond order of 2. Now, one other thing that I want to cover in this video is vocabulary and how we describe 2 specific orbitals for different molecules. And the orbital that we're talking about can change, but we use labels for the lowest unoccupied molecular orbital. In this case, the lowest unoccupied molecular orbital is the sigma star orbital. This is abbreviated as LUMO, the lowest unoccupied molecular orbital. This means if we have electrons adding into the molecule in a chemical reaction, they could occupy that sigma star. Or if we excite an electron, it could occupy that sigma star orbital. So we have the lowest unoccupied molecular orbital, or the LUMO. We also describe the highest occupied molecular orbital. In this case, it's the pi star, the 2p pi star. So we say this is the highest occupied. Highest occupied molecular orbital, abbreviated as HOMO. So we describe the HOMO and the LUMO, 4 different molecules, and what specific molecular orbital aligns with these 2 descriptions depends on the different molecule. If we have a different number of valence electrons, we'll have a different orbital as the HOMO, different orbital as the LUMO. We will end this video there. Thanks, everybody.